everybody. Welcome to the Cine talk. I hope everyone is doing well today. Is this last one a presentation before the Cine event, and I have one comment before the Cine talk of today. First, internal registrations has ended, but if anyone have the intention of anyone of Cine member have an intention to participate, please get in touch. And let me introduce myself. My name is Rafael Vicentini. I'm working with Professor Hudson and Professor Gustavo since 2017. Today, Professor Hudson and Gustavo will not be able to participate, so I will host Professor Renato. And Professor Renato is a great specialist in electrochemistry and computer simulation. I have been working with the last 2 years. He obtained his doctorate at UFSCar with a period at the School of Chemical Engineering and Advanced Materials in Newcastle University. He is adjunct professor in the Department of Chemistry and coordinator of the Computational Materials Laboratory at UFMT. So today, Professor Renato will give a presentation for us, and the main theme is computational modeling, electrochemistry, material science, and the study of energy storage material systems. So, now I give the floor to the Professor Renato, and let's go.
Thank you, Rafael. Thank you very much indeed for your kind introduction and for all the Cine committee inviting me for this lecture today. And what a pleasant morning, isn't it? Talk about science. And today I would like to talk about, let me share with you. I hope everything okay with the presentation, isn't it? Everything okay, Rafael? I hope so. So today I would like to talk about three main branches: materials modeling, electrochemical, and materials science study of energy converter for storage and related materials, related energy storage system. And as Rafael told you, my name is Renato Garcia Freitas. I'm professor at Federal University of Mato Grosso, and I'm coordinator of Laboratório of Computational Materials. Well, once that all of us work with energy conversion, many of us are used to with kind of quote. Let me remove this thing here. Like uniting the road to tackle the climate change. Well, the climate change has been a very big field and has been discussed in various spheres of the society, especially in the academic. So many of us have been seeing this kind of movie here, as we see that the increase of the temperature of the last 5 years in the hottest 5 years of the record up to 2018. However, the last year was the hottest and less compared to the end of this presentation. But few of you may know this kind of figure here, unfortunately, published in Nature Communication. In this figure, it's possible to see, as the authors used to say, black carbon dots, not a dots like a sub-dimension in physical chemistry used to say. The carbon dots because it's like a spheres. And these carbon dots in the Nature Communication, the authors used to say black carbon dots like, in Portuguese, general translation, like the fuligem. And what you have here, if you take a look in this red part of the field of this image, like this part here, this part here as well, here, we have fuligem, black carbon dots in the umbilical chart. Yeah, isn't it? We have fuligem in the umbilical chart, and we have several damage for the new babes, several kind of deaths, unfortunately, and like deaf, dumb, and blind for new babies as well. So we are used to the climate change, and we are just for the hottest of the weather, many kind of this kind of things. However, this one is very, I think that is kind of new for many of you, and it's very important as well. So another kind of extremely massive, important thing concern the climate change. And to concern this kind of problem, we have to study. We study energy and storage energy system, like stored energy materials and conversion energy material as well. And for the kind of system, we have a bird's eye view of computational material science. What we have here, if you take a look in this axis, we have the time, like femtoseconds up to seconds. And in this part of here, we have the length of size, nanometer, micrometer, and millimeter. What we have here, I would like to narrow the band gap between experimental guys, researchers, and theoretical researchers. We'd like to say all of us are researchers, isn't it? And all of us would like to work in the same target, energy conversion. So we need to narrow the band gap between experimental science and theoretical science. And to do that, we need to pay attention in the time constant. What the time constant of your system? Suppose you are experimental and you are studying some system. What the time constant of your spectroscopy, of your experimental data, isn't it? And suppose you are a theoretical, a computational chemistry or physics or a computational materials modeling. What the time constant of your method of computation? Here we have the three main branches, like this first one, quantum mechanics, isn't it? Quantum mechanics, we have couple cluster, for example, density functional theory, and we have for couple cluster, is an extremely massive kind of computation where you have tens of electrons, system very filled. In general, the first, second, third line, the chloride, for example, has 17 electrons. It's too much, so a very narrow kind of system, isn't it? Molecules very narrow and few electrons concerning that. In density functional theory, we don't have wave functional theory in this case, like couple cluster, wave function method. It's the density functional theory. So it's possible to study a little bit larger and the other kind of properties, like in this case, we have a semiconductor and organic absorption, and we have orbitals in this case, and the injection of some organic molecule injecting in this semiconductor, for example. And in this kind of new kind of method here, we have molecular modeling. Concerning molecular modeling, we have like a protein in this case, we have some Brownian molecules like in this case, and we have all atoms, molecular dynamic, implicit solvent, molecular dynamic. Remember that we have implicit and explicit solvent, molecular dynamic, coarse grain, molecular dynamic, and Brownian dynamic as well. And we have hybrid methods like the joint of quantum mechanics and molecular mechanics, like QMMG, quantum mechanics and molecular dynamics in here. And the third, we have continuous method, like finite element method. So in this case, we have some porals of a battery or a supercapacitor as well, and the charging for 4.3 volts and discharging here 3.5 volts, isn't it? So I would like to show you some papers in here and some studies concerning these three kind of methods and how can we looking for some experimental data in the joint experimental and theoretical data. So take a look and remember that one. Quantum mechanics, couple cluster, DFT, molecular modeling, and molecular dynamics in here, and continuum method, finite element method, all right? And our laboratory, as the name used to say, Laboratory of Computational Method, Computational Material. So used to study this kind of branching here, computational details, the general computational details that used to work is. For materials modeling, in general, we use density functional theory, molecular dynamics, and a little bit of finite element method, all right? For material science, we use only read-field refinement. There are several kinds of techniques concerning material science, but we use a lot of read-field refinement. In electrochemistry, we are fascinated for electrochemistry, especially for electrochemical impedance spectroscopy, using transmission line, all right, transmission line model. So can you imagine, yes, it's a computational materials laboratory, but you work with electrochemistry and you have impedance. And impedance is obtained, of course, we can obtain impedance theoretically, but I will show you some data here, and this impedance was obtained experimentally. And how this experiment was obtained? All of them, experimental data. All data, take a look here. All data belong to my co-workers. We have a strong frameworks with our co-authors. So we used to modeling this kind of system concerning materials modeling, material science, electrochemistry, and all experimental data. If you take a look at, you'll see a lot of experimental data here. all of them belong to my coworkers, which I must express my grateful because we have this joint concern theoretical and experimental. Sure. And I must express my gratitude as well for our secretary in the Federal University of Mato Grosso, because we have this server, it's our cluster here, where we located all of our workstations, because we have several problems concerning universities, isn't it? We have a massive electric demand, and the network doesn't comport, not yet. So we have a lot of shutdowns. So now we are avoiding this kind of problem, put our workstation here in the UFMT main building on the Secretary Information Technology, and they have massive no breaks and a generator as well. So if you have some shortcut, for example, we have no breaks and diesel shortcut generator as well. We have an account in Senapad, and in general we use for material science, ritual refinement, GSAS, General Structure Analysis System, Gaussian and Gromux for electronic structure, console for finite element method, electronic structure as well for using quantum expressor, and some routines using machine learning, artificial neural network using MATLAB. MATLAB and R as well. We have a lot of scripts building on R. All right? And remember, quantum mechanics, couple cluster, DFT, molecular modeling, molecular dynamics, and continuum method, finite element method. So the first paper I would like to show you here is this one. Consider the Nobel Prize in Chemistry in 2016. The Nobel Prize in Chemistry in 2016 was shared between Jean-Pierre Sauvage, Professor Sanfrecce Estudo, and Bernard L. Feringa for design and synthesis of molecular machine. So when people have some organic molecule like this one, and you have separated different wavelength, it's possible to change the conformation of this organic molecule. We have a molecule like this one, in this shape, in this one. So we have like nano machines, like nanomolecular machines, as you can see here. And Professor Bernard Feringa is a strong co-worker with Professor Dennis Jackman. Professor Dennis Jackman stayed here with us for around 10 days, and it was a very fruitful time during that time. We studied a lot of time domain, density, functional theory, and we scheduled some kind of computation we used to do during that time to publish a paper. Indeed, we published a JCPC, isn't it? With Cynthia. Cynthia was this little girl, was responsible to study 41 organic molecules, electronic spectra for absorption, and 36 exchange correlation functional, as you see here. Take a look. We have a benchmark, a cross comparison between experiment, time domain, density functional theory, and wave functional theory, wave function methods. So we have a benchmark concerning 41 organic molecules. We take a look in 41 small organic molecules with different chromophores, and take a look in the literature, because we don't have experimental coworkers in that time, for absorption energy, and take a look in experimental spectroscopy magazine journals, and 36 exchange correlation for TD, DFT, 9 wave function methods, and in general, the level of theory was Gaussian. We used Gaussian 09 at that time, and TD, DFT, BTRLE, AUG, CCPV, KZ, pay attention, CCPV, KZ, and we explored at that time 6 states, excited states. Wave function methods, the theory we use Dalton, C4, and just a little bit of Psi as well. So what do we have in this graphic here? We have, for example, nuclear position of the ground stage. Suppose we have the ground stage and have excited states, as we see here. In blue, we have the vertical absorption energy related to first excited state, like here. We have this Jablonski plot, and we have a dynamic of relax for this excited state, and we have here the first excited states. Here we have the energy in orange, the reorganizing energy for excited states. Here we have all the theory concerning Marcos theory as well. In red, we have vertical fluorescent energy In purple, we have the 0, concern EC1, EC0, and adiabatic energy, all right? And we can subtract the 0-point vibrational energy, all the one for this part here, and this part is here as well. And this table, we have, take a look, the adiabatic energy for wave function theory, couple clusters, singlet, doublet, triplet, CC3, CCSD3, and here we have DFT for TD and DFT, B3, bacterial young par, isn't it? B3 LEP, and CAM, cooled attenuated method, B3 LIP. If you take a look for, we have several errors concern the adiabatic energy, medium square error, MAA, RMSA, but take a look in this part here. The percentage of AE, acceptable error. We see, as expected, that wave function theory concerns CCSDT, CC3, CCSDT3, all of them concern 100% of acceptable error, all right? Compared to experimental data. However, if you take a look for DFT, TD-DFT, I mean, B3 LEAP, CAN B3 LEAP, we have 46% for B3 LIP, and for CAN B3 LIP, we have decreasing acceptor error, 29, almost 30. And maybe you see, but professor, the CAN B3 LEAP, isn't it? We have the CAN, it's another generation of B3 LEAP. If you remember B3 LEAP, we have 3 experimental parameters for the back Ling par, isn't it? We have the CAN, the cooled attenuated method. We have the short range for hard 3 part, the long range for the hard 3 part. Would you expect it would be better, isn't it? But not, because B3 LEAP and CAN B3 LEAP would parameterize it for angles and bond length of organic molecules. In this case, we don't have a better acceptable error for CAN B3 LEAP as we expected. So if you take a look in this part, we have medium square error here, medium average error. In this part here, we have wave functional theory concerning experimental 0000 energy. So we have CC3, CCSDT3, all of them, a very small kind of error. You see here, very small, CCSD3 is small as well. And all of them, 31 exchange functional increase the error. You see here, we have them famous B3, Ling par, like here, PBE, take a look, small error here. Período of 0 here, isn't it? Even for Minnesota, which is very famous, Minnesota M062X, Minnesota 06 hydrophog, we have an increase in the error compare separate kind of molecules. The chromophores, one kind of error, the energy of the excited states, another kind of error, and another kind of thing we have the kind of organic molecules. So we have LC, BILP, LC, PBA, and CAN B3 LEAP here as well. So if you like to perform some excited state computation, for example, you have the chromophore, pay attention to the chromophore, you take a look in this table, you take a look in this kind of energy would you like to measure, for example, vertical absorption, fluorescent absorption, adiabatic energy, excited state organization rate, or for the excited state from the ground state, and here is a guide. We have several other kind of tables as well, but this paper is a guide for you kind of molecule, kind of chromophore, and the main density functional theory can you use compared to large and very expensive wave function theory method like all of them, which have an improvement in the error for sure. But here we lost affinity accuracy in the percentage, as you see here, isn't it? But we have improvement of the performance of the computational time concerning the density functional theory. All right? And in this paper, the team of Professor Zanin synthesized using a very special technique pentox niobium oxide and carbon nanotubes. So you take a look here. We have carbon nanotubes and niobium oxide. The niobium oxide nanoparticle is around 90 nanometers, as you see here, and they perform the X-ray diffraction. So Professor Zanin talking with me, hey, Renato, we have the X-ray diffraction, have some impedance. Could you take a look in this data and see what kind of simulation we can do here? So first of all, we perform the heat field refinement, as you see here. The heat field refinement is not well oriented, as you see here, because we have a decrease in the Cine profile, isn't it? And we have two kinds of reflection for the Spartan. We have orthorhombic 3 niobium oxide, like this part here, orthorhombic crystalline structure, and we have this phase as well, the monoclinic niobium oxide. So you see, here we have 101 monoclinic niobium oxide, and here this long B-axis, we have orthorhombic niobium oxide, isn't it? And the crystallography parameter, as you see here, ABC, lattice parameter of beta gamma, lattice parameter, and pay attention in this part, particle size. The particle size 70 concerned for orthorhombic plane, orthorhombic niobium oxide is larger, 70, compared to monoclinic, 52. The lattice strain concerned for orthorhombic is lower, 0.2 concerned with 0.31 for monoclinic. And we have a large fraction of this phase here. You see the fraction of 0.61 for orthorhombic and 0.38 for monoclinic. What's the main point here? If you take a look in the C-axis of the structure, we have C101T niobium oxide. If you take a look in this part, you see the channel where we can insert and during the charge and discharge sodium ion. And the Professor Zanin and his team perform a very special kind of material, this one, because it's possible to use the sodium ion on the supercapacitor, pseudocapacitor in this case, and in battery as well, as you see. And why sodium is so important? If the interplanar distance for 101.8, which is monoclinic niobium oxide, we have 3.8 angstroms, and the lattice of the 1001 orthorhombic niobium oxide is 3.9. So we have an increase in this one, increase from 3.8, 3.9 in the lattice, the plane from 101 to 01, and it's important because the Stokes radii of the sodium, which means that we have sodium and water molecules, is a little bit larger compared to lithium, which is most studied, isn't it? All of many batteries nowadays is studied using lithium. So we have the radius for sodium ion is 1.02 angstroms, which is larger compared to radius, Stokes radius of lithium. It's 0.76. And we have this kind of electronic properties. We see here a fingerprint of the charge discharge of pseudocapacitor. Is very triangular, isn't it? Electricity resistance in here that is not possible to see, but we have a fingerprint of a capacitor like this one for carbon nanotubes, for niobium oxide onto carbon nanotubes, and you see the fingerprint as well of a battery. Take a look here for the discharge and for the charge. So we have the same kind of materials. And I mean, it's not an electrochemical cell, it's a coin cell indeed. It's a button cell and a PET cell that guys can construct as well. So we have for the same kind of materials, carbon nanotubes and carbon nanotubes plus nanoparticles of niobium oxide. It's possible to perform pseudocapacitor studies and battery studies. If we take a look on the radial plot, we see here electrical double layer capacitors, all this part in here, and here we have lithium batteries, nickel hydride, sulfur kind of batteries as well. And these materials synthesized by Professor Zanin's team is in the middle. Yes, amazing, isn't it? We have electrical double layer capacitor, battery, and these materials is in the middle, like observe here. And we have a fingerprint of supercapacitor, pseudocapacitor here, and a battery as well. And for sure, it's a charge discharge. And the guys used to do charge discharge for 1,000, 10,000, 100,000 charge discharge cycles. And the battery and the pseudocapacitor stay and keeps stable. So in another study, we pay attention for the impedance. Take a look. Electrochemical impedance spectroscopy. And in this case, we have the transmission line model, because for here, we have anomalous diffusion. Let's pay attention. We have anomalous diffusion. If you study impedance, if you know transmission line model, anomalous diffusion, you'll see that it's clear possible to observe here that we have a transmission line down here and a transmission line here. Well, we have three main kinds of Warburg diffusion, isn't it? But to be honest, we have five, but the two others deserve another 42 slides. You can invite me further. But we have the main three. We have finite space Warburg, isn't it? You have finite length Warburg, and they have Warburg semi-infinite diffusion. In the first case, for example, we have finite space Warburg. We have a cotangent hyperbolic dependence. So suppose you have a 45-degree slope of impedance, and you increase. It's a cotangent hyperbolic dependence for finite space Warburg. In another case, when you have a 45-degree impedance, it's a Warburg, isn't it? And we have a semicircle in here, we have a finite length Warburg. In the case where we have, suppose, if the length of diffusion is lower than electrolyte resistance, we have, people used to say, the open Warburg, isn't it? In this case, we have reflective boundary. For example, when we have the reflective boundary, people used to say in the textbook that electrode, the pores is blocking. In other words, it's impermeable, isn't it? In another case where we have the increase in a short, in the semicircle like this one, we have the finite length Warburg. And suppose we have the length of diffusion higher than electrolyte resistance. So we have the length of diffusion higher than the electrolyte resistance. We have a transmissive boundary. If you have transmissive boundary, suppose that this electrode is permeable. It's a non-blocking electrode. So if you take a look here, all this impedance, I must stress out this part, that all these both impedance were obtained in the same range of frequency, isn't it? So if you have the transmission line here in the higher frequency compared to this one, which is shifted to the lower frequency here, you have separate profiles, isn't it, compared to the impedance in the Warburg one. And once that the frequency is equal 1 divided by period, we have the time constant of diffusion different, all right? All of them will have a semicircle in the low frequency and the transmission line in the high frequency, as observed here. And to fit in this model here, we use a transmission line. As you see, we have a transmission line and we have a porous. When you have a porous, you have a sinusoidal wave that we use to obtain the impedance. And for a very large, a very small porous, the mouth, the top of the porous, it's blocking, acting like a blocking for the wave impedance. So we have a dump, like a dump wave of the impedance. It's decreased the dump of the profile penetration of the wave from here on the electroline up to here in the back. So we have problems of anomalous diffusion in this case. And we have a statistical two-channel transmission line. And we have the C1 here, the C2 here, and the interface elements like obtained here, and the polar here and here. That's the solid part, that's the substrate, and the transmission line parameter here observed was the key quadrant, the statistical parameter was pretty good. Mutual carbon nanotube, niobate oxide, and we have, pay attention, the electrolyte resistance looks similar because it's the same, isn't it? 7.1, 8.8. The resistance of porous, this part here, the resistance of porous was obtained for mutual carbon nanotube 60, and mutual with nanotube oxide is 20. Just a little bit decrease for mutual carbon nanotube may relate to the ballistic conduction properties of the nanotube, as you know. The capacitance, as you know, we use the CPE in this case, the capacitance of double layer 3.1, and the increase of the capacitance here for mutual carbon nanotube, the hybrid material with mutual carbon nanotube and niobate oxide, 3.1, 5.06. The phi, also called as alpha, the parameter of the CPE, is 0.997 and 0.95. As you know, if we decrease the alpha values, it's related to a more crowded species in there and related to the fractal dimension as well. So probably we have a decrease 0.97, 0.95, because we have more species, like in this case, sodium ion, in the Letzi parameter of the niobate oxide for orthohomologic monoclinic parts, is obtained here. A large decrease in resistance, the charge transfer resistance, as you see, 49.7, 70, and 1 order of magnitude decrease concerning the resistance of material. Take a look, 3.5 and 0.3. It's massive. It's massive. That's because it's possible to use this material here, which is niobium oxide, mutual carbon nanotube, as battery and as supercapacitor as well. All right? Another paper I would like to show you is this one, cadmium selenide into titanium oxide nanotube. Experimental and theoretical study. This paper is not the highest impact factor that we have, but probably is I love this paper because probably is a really good example how to use several kinds of modeling to explain electrochemical properties, like an electrochemical problem, in this case, the diffusion and electroplating, and we apply this electrode, in this case, for water splitting. What we have in this paper, a foil of titanium. When people used to anodize titanium plate, a titanium, normally, we have titanium nanotube, right? When you have titanium nanotube, you withdraw titanium plate from the solution. We have amorphous titanium nanotube oxide, isn't it? If you take a look in some X-ray diffraction, we don't have the partners of anatase and rutil in there. It's need to thermally treat to evaporate water and obtain the ceramic, the inorganic part of titanium oxide. So we was wondering, let's deposit cadmium selenide. Cadmium selenide is a fantastic kind of semiconductor because it's a narrow band gap, 1.8, 2.2 electron volts, for example. We have titanium nanotube with titanium oxide. Anatase and rutil 3.2, in general 2.8 for anatase and rutil as well. But we have a problem. We would like to electroplating cadmium selenide. And how to electroplating cadmium selenide inside the nanotubes. If you take a look here, we have previous thermal treatment. We obtain the titanium nanotubes and previous thermal treatment, and soon after deposited cadmium selenide, or later thermal treatment, we obtain titanium nanotube oxide, or deposition cadmium selenide, and calcinate soon after, all of them together. And in both of them, if you see here, we have the nanotubes, and this part here, previous thermal treatment, A, in B, later thermal treatment here, and you see the top of the tube, all of them is opened. You see here, opened. It's a fantastic way to obtain junction. In this case, titanium oxide is an anytime semiconductor, cadmium selenide is an anytime semiconductor, but we did this kind of study for ruthenium oxide, it's a P, so we have a junction, a PN junction, and you know, when we have a PN junction, we have a ohmic drop, isn't it? We have an injection of this part of the other part for short parameter, short barrier, and this kind of thing. And how it's possible to obtain cadmium selenide under pulse electrodeposition? It's a very simple task. You need to solve the Fick law, the first and the second Fick law. For example, cadmium selenide in the electrolyte solution, we have cadmium cations and selenide anions. So we have a pulse of a positive potential. We have selenide inside the nanotubes and another pulse on a cathodic valence. So we have cation in there. The positive selenide in the nanotubes, negative cation there. So the cation and selenide react inside the nanotube. We need to vanish all the species from the solution, get inside the nanotubes reaction, when we must vanish the concentration here and take another pulse as well. So we have indeed hundreds of pulses from cathodic, anodic valence, cathodic valence, anodic valence, cathodic valence from a species in there and get inside. Soon after, we perform some heat field refinement. Again, using general structure analysis system, pseudo-void, and Tom-Cox-Hastling was the function. If you see here, the heat field refinement, in this case, we have a preference horizontal kind of material for previous thermal treatment compared to later thermal treatment, and we have the crystalline parameters AC, because it's tetragonal, AB equal, C different, and crystalline size 297, 316, and the strain, take a look here, we have a 0.47, the strain for PTT, and the 0.54, the LTT, all right? If you remember, we have opened nanotube in here, and it's a tough task concerning the electrochemical kind of measure, obtain this one. And for several years, it was a problem, how to solve this problem. Why? When you put some titanium nanotubes of aluminum, for example, nanotubes or nanopores inside a solution with some cation, would like to electroplating, and apply the position, we have the blocking surface. We have deposited onto the top, not in the bottom, because Professor Ernesto solved this problem, pay attention, in 2008, using finite element method concerning electrodeposition problem. If you take a look, we have the anode here, the cathode in this part, we have a dielectric species increasing here because titanium is a metal, titanium is a conductor, all right, but it's not the titanium what we are working here, it's titanium oxide nanotube. So we have a titanium, we have a nanotube, which we can control up to micrometers, and the tube around nanometers, for example, and we are plating cation selenite or any species, or even polymer, it's possible to deposit polymer as well. Not on titanium, we are depositing species on a dielectric, on titanium oxide, and we have a decrease on the conductivity, isn't it? So we have the solution here and the pore. The model using finite element is this one. If you pay attention, the diffusion profile, we have a diffusion profile in here, 0.99, again, 0.96, 0.93, 0.8, 0.7, 0.6, 0.5, 0.4. As you see, the diffusion profile looks like it's spherical and is higher in the top of the tube. That's the main reason when you electroplate in something, it's blocking the surface. That's why we need to use the pulse electroposition technique, anodic and cathodic, anodic and cathodic. All right, to obtain cation selenite. And in the top of the bottom here, when we have a large part of this dielectric species, like titanium nanotube oxide, we have a massive decrease in here for the diffusion profile. If you take a look at this part, the top of the bottom of the tube, even from the bottom here, we can divide in three parts, the 3, 2, and 1. And take a look in this part here, we have the relative voltage drop. The voltage drop concerns three parts, the top and the bottom. And we have in the top, the unity of the voltage drop, as you see this part, 3. In the middle of the tube, or in the pores, for example, we have this part, and in the bottom, we have this part for relative voltage drop. That's the main explain. That's the reason it's very difficult to deposit something inside the nanotubes, or in this case, aluminum inside the nanopores as well, and we need using pulsed kind of technique. If you pay attention, we have an electroplating kind of problem concerning oxides, pores, and tubes in phosphoric acid, I think, yes, and published in 2018, Eletroquímica. And 1 year after, I mean, at the same time, use the same kind of system, the same problem, use the same methodology, finite element method. 1 year later, voila. We have Nature Materials with Professor Herbert, when he solved this kind of problem as well for aluminum as well, and another branch of electrolytes, phosphoric acid, oxalic acid, and sulfuric acid, I think, as well. So in this case, we have self-ordinary pores and finite element method. If you take a look at this part, we have higher tension here. We have a color map, 35, the increase of the voltage, decrease of the voltage. As you remember, titanium oxide is a dielectric, it's an oxide. Titanium is a metal, titanium oxide is a dielectric. So we have in the bottom, increase of the voltage here, and in this part of the tube, for example, we have a decrease of the voltage. Large currents, the plot of the currents in this way, And here we have this strain, and this strain is related to the angle of this tube. For example, here we have high strain compared to this part. We have a strain, the color map red. This part here, you see a large strain in this part compared for this one here, and we have the arrows, the flux and the velocity of the ions electrodeposited. In this case, the oxygen get inside to aluminum, titanium oxide, to obtain the dioxide. All right? And if you study, for example, water splitting using AM 1.5G, you see this profile here is the electrochemical cell, and we have the both. Cadmium selenide into titanium dioxide nanotubes, PTT, previous thermal treatment, and in red, cadmium selenide into titanium dioxide nanotube here, later TT, LTT. If you take any potential in this part here, you see that the lifetime for the water splitting using the Professor Bisquet and Arias-Aban approach in this part, you see that all the lifetime is decreased compared for the LTT compared to PTT. All the PTT, previous thermal treatment, obtain slow strain and the increase of the water splitting. For any potential like this one, you take a look here, we have this part, and in the black curve, we have this part here as well. All right? It is another paper. It's concerned titanium dioxide and titanium dioxide ion doping nanoparticles. A friend of mine told me, hey, Renato, I have a new material, titanium dioxide. And I said, which material? Yes, titanium dioxide. I mean, hey, guy, it's not too new. You need to read a little bit more of the literature. It's a very no material. No, but this one with doping around 5% with iron. Yeah, and you obtain the activity for the kinetic of degradation for rhodamine. In this case, for example, is massive. I don't remember how many orders of decrease, the increase of the degradation the guys obtained for titanium dioxide iron doping here compared to P29. And we have the GUSA. That's the main titanium nanoparticle using in the industry, isn't it? In this part. So the reactor here, and what you can do with this kind of thing, they have the X-ray diffraction. We perform the heat refinement as well, and we did some electronic structure using quantum expression. So in this case, remember couple cluster DFT, but DFT in this case we use the Hubbard cohesion, because we have the problem already know from the density function of state, then density function field concern that underestimate the band gap values. And the band structure of density of states in this case, we have from anatase, the root field, the M gamma indirect transition, band gap 3 electron volts. In this case, we have gamma M 2.1 electron volts. Then we use ultrasoft, so potential per Delvang 91, plus Hubbard 5 and 5.5 for titanium in the anatase, and 5.5 from root field, and some electronic structure parameters here from the computation, isn't it? If you take a look, without Hubbard correction, we have a band gap from 1.3, PW91 plus U, I mean DFT plus U, we have 3, DFT 1.58 from titanium dioxide doping, in titanium pure, only titanium, 1.58 for M gamma, PW1, and DFT plus U 3.1 from anatase, and from root field, we had 1.3 with 5% iron doping, and correct, but DFT plus U 2.1, 1.4, and 2.5. Using zero Conning approach, how to correct the appropriate value of Hubbard for your system. So we must, in this case, use a supercell. So we have a supercell in order to withdraw one titanium atom, put one iron atom, and obtain the doping rating of 5%. So we have this kind of supercell here. In this case, anatase, titanium oxide anatase, in this case, anatase, iron doping. You see the red one, it's an iron doping. And here we have root field, titanium oxide pure, root field, and in this case, iron doping as well. For sure, I will not show here, but my student studied all these possible sites to dope and decrease the energy for this doping, in this case, iron. Another problem, in this case, we have LSDA, we have a non-parallel spin from the iron, so we have to take into account the magnetization of this part. So we have here the p-dose, as it's possible to observe large contribution of oxygen here in the valence band, in the conduction band titanium, and you see we have titanium 1 and 2, I mean the first layer of titanium and 2, the second layer of titanium here, almost the same, and we have the doping of iron here. We have the split because we have unparalleled electrons like Handy rule, and we have oxygen, more contribution of valence band, and titanium, more contribution of the conduction band. And in this case, we have the split of the contribution of titanium. You see the titanium red, I mean the 2 in this case. Here increase, and in this part titanium is decreased. It's because the local energy entropy, we make it as well. We made a computation, and you insert iron doping in this part, it induces a strain in this part, in nearby atoms like titanium. So we have this kind of difference of the contribution. In this case here for refill, we have higher contribution of oxygen in here, different parts in this way from titanium in the conduction band. Here is the same, large contribution of oxygen in valence band and higher contribution of titanium, and you split this part as well, the contribution of titanium from the first layer where the iron was doping, and the titanium from the second layer as well. And concerning the bond structure, we performed the Kronig-Penney model, and we see here we have a indirect bond gap like M gamma in here, and we have the Xi gamma like indirect band gap. I mean, if you have an indirect band gap, we have a phonon in the lattice of the structure, and we have the increase of the effective mass of electron and hole. Suppose you have a semiconductor and you have a wavelength as enough to have the electron in the conduction band. As soon as we have an electron in the conduction band, we have a hole in here. Electron is negative, hole is positive, and the mass of the hole is higher than electron. It's already know. So we have from anatase, we have 1.6 effective mass, and an increase from deuterium 2.5. Doping with iron, we have effective mass 0.24, and increase 0.53. All right. The same from the hole, as you see here, from anatase pure 0.32, and the ruthenium 0.86, and hole from titanium doping 0.38 and 0.64. I mean, we have an increase in the electron effective mass and the hole as well. So we have the higher active for anatase in this case, the titanium oxide. At last, we perform some nude electric band, so NIBI. We perform the several steps of reaction. In this case, we have the water absorbed onto the surface of titanium oxide, and in this case, titanium oxide, and here, titanium oxide iron doping, and is split one hydrogen absorbed in a titanium, and you have OH, which is released to the surface. We have OH dot, which is oxidative species responsible for degradate. In this case, it was rhodamine. Yeah. So it was impressive, this result. Take a look here. We have the anatase, and we have all images obtained here. Here, the doping one from anatase, and here we have almost two main determined step reaction, like in this part, 0.34 electron volts at activation energy, and this one from transition state, we have almost 0.3. It's a very massive, large value, 0.3 for only for anatase, pure titanium dioxide. And here from titanium dioxide iron doping, we have decreased from less than 0.1. As you see here, take it one image state, first imaging, and the last imaging, initial state, the final stage, the transition state, and we don't have several steps like in this case. In this case, we have the oriented water split and the absorbing. In this case, no, we have only this part, a decrease, a lower absorption energy for OH, large distance from the titanium and even iron, from the oxygen and H, from hydrogen as well, and it became easier to release the OH species in this case. It was an impressive result as well. So we have the couple cluster, isn't it? We have soon after TDDFT, TDDFT plus Hubbard, like in this case, and quantum mechanics, and now we have molecular modeling. In this case, we studied the supercapacitor and radius of cations using molecular dynamics. We're using a constant concentration, like 1 mole liter minus 1 of methyl sulfuric acid, isn't it? Where M we see lithium, sodium, potassium, rubidium, cesium, like we have here. Graphene electrodes, the level of computation, lamps, water, first field here. In this case, we have single point charge, and OPLS, optimized potential liquid solvent here, simulation. What else? Here, if you take a look, we have lithium, sodium, potassium, rubidium, cesium. It's possible to observe that we increase the radio, yeah? It increased the rate of the anion. In the high school, we know that. In the first year of the university, you know that as well. That increase the rate of the periodic table will increase the radio. But the Stokes radio decrease. The rate of the water absorbing these species decrease. So we have a dynamic of electrochemical double layer completely different in this case. And it's very impressive. If you take a look in this part, we have lithium, sulfuric, lithium in this as cation, potassium, and cesium. All of them sulfuric, as you see here. 0 volt, minus 0.6, 0.6. If you take a look at 0 volts, we have the shift in the band of the cations, as you see this part here. It increased this place for this part because we have the change of the signs of the lithium, potassium, and cesium, all right? Here, concerned to the face of the electrode, the 0, center at the 0, we have almost electrical double layer 1.5. And the sulfuric acid, we have the density species like presented here in the distance. We have displacement because it's like a GR, the coordinate generator of the distance. We have this part in here. At minus 0.6, we have, pay attention, if you have a negative electrode, so we are target positive species, so that's the cation. We have this kind of dynamic in here, where we see the shift of the potential as well, and the density of states, this part here. And at this one, the other part of the electrode, see 0, minus 0.6, at plus the positive electrode. If the electrode is charged positively, the negative species is targeting there, because electrode static attraction. So in this case, we have sulfuric. The sulfuric crowded water is possible to see a very few difference in this case, like observed here. The density of states, the density, the who, observed here, here, and here as well. And here they have the charge fluctuation of the electrode. Again, we have negative electrode and positive electrode. So the negative electrode face to cations, isn't it? Lithium, sodium, potassium, rubidium, and cesium. And the positive one, we have the sulfur anion in this part. If you take a look, if you decrease the series 1,8, if you increase the radius, isn't it? Increase the radius, it means we have the largest spot in here because we have decrease from the negative values to the positive. I mean, if we are negative electrode and you have cesium face to the electrode, guys, it's electrochemical double layer. I mean, if you have the negative electrode, you have a spot part in here, and it's not well defined because we have another here, another part in here, another here, and another part in here. And if you take a look here, it's crowded of brighter concerned to the 0. In this part here, concerned to this one, because the radius, the Stokes radius of lithium is smaller compared to the cesium, isn't it? And also we have specific adsorption of the sulfate, like in this case, you have the sulfate here, almost blue. I mean, the electrode is positive, electrode positive. We face the sulfate in there, isn't it? However, the lithium is quite low, so we don't have specific absorption here. As a result, we have a target almost blue in this case, because positive here. However, for this kind of electrode here, we have a -1 face to the sulfuric anion, and we have the cesium, which is a large ion and a lower Stokes radius. We have all these partings. The blue, the positive, goes to the zero. I mean, we have the electrode positive charge, we have the double layer, we have sulfuric species in there, you know, the electrical double layer, we have Helmholtz plane, internal, external hub, we have good Chapman, we have Stern, we have all of them. We don't have a decrease, a linear. We have a linear in the first step, soon after we have an exponential, because they will have absorption. And that's we see here, the absorption of sulfur anion and cesium as well. So beautiful, isn't it? Finally, we have induced electrode distribution, in this case at 0 volts, in this case minus 0.6 volts, and from 0 volts. Let's see 3 main differences: lithium, potassium, and sodium. And so you have lithium, the black one, it's lower than the 0. The 0 is the dense charge, the neutrality. So we don't have, if you have a peak lower than neutrality, we have absorption, specific absorption. So we have lithium here, potassium a little bit decrease, and the cesium. The cesium we have large anion, but the Stokes radius decrease. So we have the shift in this part in here. 0. It's not charged electrode. However, as soon as we apply minus 0.6, a negative electrode, in this case graphene, a negative electrode, we face to the cations in the dynamic of the surface in there. So we have, in the first case, lithium here, the potassium, the electrode is negative, so we have a positive anion dynamic to that. Lithium here, potassium down there, and cesium decrease. Because cesium is a large anion, the diffusion coefficient belonging to all of them is quite different, and we have a width of this Gaussian is quite larger because the cesium is larger. All right, so we have couple cluster, DFT, quantum mechanics, molecular modeling. This paper brings the example of molecular dynamics as well. And we have this last example from the capacitance for lithium, sodium, potassium, rubidium, cesium. In this case, the contribution different from the negative and positive electrode and the integral capacitance. It's possible to see that all of the blue part of the positive electron, when we face positive electron, we face the sulfate is almost the same, like this here, and the negative one. The negative, if you have a negative electrode, we face the positive electrode, the positive anions, in this case, lithium, sodium, potassium, rubidium, and we have an increase in the capacitance because we've increased the radius. However, the Stokes radius decrease and the diffusion coefficient increase as well. So we have an increase up to there. In this case, from potassium, we have the d orbitals, and you have a large system, and we have a blind. It's not a blind. We have an effective potential difference from the core, from the electrosphere of potential as well, because we have d electrons, and it decreases again, isn't it? Perfect. A very joint between electrochemistry and theory, computational electrochemistry one. And the integral looks like the same, isn't it? Because we have the integral capacitance from negative and positive electron. This paper was published with Professor Fillet and Professor Woodson as well. It's co-workers. And in this part, going to the finite element method, we need to discuss just a little bit about the pore. The first time the guy coined the term pore in the impedance, concerning transmission line impedance, was 1960. It's not new, 1960. It's a German paper. All of them, many authors belong to the transmission line and the pore of the electrode. Get started with Delevi, because the Delevi published in English, but Euler published in German in 1996. So if you see here, Kaiser published in 1976, the geometry, how the geometry of pore, the morphology, affect the impedance. So we have this impedance 1, this pore, impedance 2, this kind of thing, impedance 3, this morphology, 4 and 5. 5, we have this impedance. So if you obtain an impedance, you have a transmission line, it's possible to take a look at high frequency, see the morphology of your pore, isn't it? In 1983, the authors studied a fractal dimension of the von Koch curve and see the dispersion of the frequency dispersion of the center of the impedance. As you see, the guy used a pure capacitor, decrease the alpha value, and decrease a little bit more. You see the plate, you see the square, like the CPE, and square a little bit more in here, 93. In 1985, the Pakowski concerned the study of the arrays of the fractals. I mean, the frequency dispersion are related to the fractal. I mean, and we have a spread of the arrays of resistance and capacitor, like here, resistor and capacitor. They suggest this one. And in 1987 here, we have the von Koch again, A, B, C, D, increase the fractal dimension, and the authors observe not only the center of the impedance, also the shift of the main values. The impedance become not circular as well, and not depressed, but also going to shifting in the impedance, in the real impedance here, because to the diffusion, anomalous diffusion obtained here affect the result, the real impedance in this part. Fine. So I was wondering, as soon as we construct I assumed the position of professor here, I was doing some density functional theory with my students, and I performed some impedance, some finite element methods as well. And during that time, I was wondering, so how to construct a fractal dimension in a 2D plane in order to study the fluxion and infer the Nash-Planck equation in there. And I was studying, have to pay attention, you need the Fibonacci series. How to construct the Fibonacci series, you know Fibonacci 1, 1 plus 1, 2, 2 plus 1, 3, 3 plus 2, 5, 5 plus 3, 8. How we have a series of Fibonacci and become that one in a 2D. And we have the triangle Pascal. And I performed some computations using triangle Pascal, and study this kind of morphology. I face it to this one, Sierpinski carpet. In the Sierpinski carpet, we have the initiator, like this part, and have the area I relate to counter plus 1 is equal 8 divided by 9 power 1. If you see 8 divided by 9, it's a value lower than 1. If you increase a value lower than 1 and increase the E, you have 0.8, 0.7, 0.6, 0.5, 4, 3, 2. As soon as you increase the E, we decrease the value. So we decrease the area. I mean, if it goes to infinity, the area of the Sierpinski carpet goes to 0. It's amazing because we have a density. You have the normal current, for example, divided by area. So we have the generator in this part. If you divide by 9 and you spread in this here, in this part here, you have the step 2. If you divide each of this part and spread again, we have the counting 3, counting 4, counting 5. All right? We have several computations concerning that. But now I have a student who performs some scripting, and it's possible to obtain this image. It's possible to crop an image from some paper, like in this case, lithium concentration of active material at 500% of state of charge. I mean, we have a battery, 500% state of charge. That's the SEM, scan electron microscopy. And my student, it's possible to obtain this image, obtain the domain, the binary in this one. And as my coworkers, we have access to the FIB. I mean, if you have the SEM, scan electron microscopy, we have a beam and a flux of electron. Electron turn to the center, you have a counter. Oi?
I have to ask you to finish in 10 minutes.
All right.
Have time to the questions and comments. Okay.
All right. So it's possible to study the part, all this part of the surface, like obtained here. So we perform some flows using finite element method, console all this part here using lithium chloride and the mesh, the relative, the normal computation. And the mesh, we have an inlet in this part, outlet, and the surface in this here. And we have some computation like time independent in this part, and dependent from 0 up to 100 microseconds at the time constant. And we have this kind of flow. We have several kinds of computation, like velocity, influence of pressure, influence of, we're trying to apply electric field as well. So we are like a circle, isn't it? We have a impedance, we have the power, we have the finite element method in this case. And probably the most troublemaking part of the presentation. In this year, Professor Holt Hoffman presented this slide in the WATOC, the largest conference of the World Association of Theoretical Computational Chemistry, and he says, the machine learning artificial neural networks have good results. It's quite cheaper, computationally speaking, and it's faster. And what is the future of quantum mechanics? Maybe the quantum chemistry, quantum physics in the future have the same destiny of the cashiers and even the taxi drivers, isn't it? So according to him, rest in peace, quantum chemistry. Because we have 4 paradigms. In the first one, we have experiment, physics law, the computational, and now artificial intelligence. And we are facing this one. So Professor Ernesto made some computation using many years ago in 1995, when we have observed this increase of the dipole moment and the jump of the polaron in the presence of water. So we revisited this paper again with a high level of computation and using artificial neural network. We performed the artificial neural network using MATLAB and R as well. And artificial neural network looks like amazing, isn't it? It's faster, it's cheaper computationally speaking, it's free. You can use that using R, using Octave, using Python. But nobody told you that the most difficult part is the hiding layer. So we use Kolmogorov, Fletcher-Claus, Vega, pyramidal, and genetic algorithms to optimize the hiding layers. Then obtain this one, the theoretical level of theory for inputs, theta, water, Grimm's correction, and the distance, and 3 outputs, the theta, between this one, here, and there. So you obtain 360 steps of decreasing of this Benzian part in here to obtain, to train the data. And we have 136 epochs, like self-consistent field, and we have amazing statistics parameter. You take a look, the train, validation, test, and all of them, 0.9994. It's really good. From the DFT, the theta, and artificial neural network, we have theta 1, 2, 3, all of them pretty good, 0.9991 statistical correction, and ANN for median square error, all of them lower than 1 for error 1, 2, and error 3. And we see that we increase up to this size, up to this scan, we have the jump of the polaron from the nitrogen to the carbon, isn't it? And this part here are concerned to spherical, like Newman project. All of hydrogen have the same molecular charge, and this part here, you see the positive and negative molecular charge, and if you face the steps of a scan, we see in this part here, almost 30 degrees, plus the initial was 104, 105, I mean, we have the jump of this polaron. It's amazing. So we study using DFT, a high-level computation, and artificial neural network as well. And finally, guys, as a main field, a main conclusion, I would like to say that computational modeling materials is a new kind of research you can use with material research, electrochemical techniques as well. We have good agreement between experimental and theoretical data. Concern electronic properties, we can use DFT, DFT plus Hubert, DFT plus van der Waals. In the case of polyaniline, we have the Grimm's. If you take a look in there, we have Grimm's Tree-Johnson correction in this case. Structural refinement is possible to perform using ritual refinement, structural properties. Electrical double layer is a really good example of how to use molecular dynamics and electrochemistry joint. All of them. Transmission line model and porous morphology can be studied using finite element method and electrochemical impedance spectroscopy, again, join the computational and theoretical computational experimental data, and artificial intelligence, AI. We can use machine learning, especially in this case, artificial neural network. And in this case, again, we have a deep layer, a deep neural network as a function of theoretical experimental data. And I would like to say, to quote again, that the famous quote, there's a plenty of room at the bottom. We discussed some example of couple cluster, DFT, molecular dynamics, finite element method, some impedance and porous, and we became again inside the porous. So we studied and studied and studied and have so many things to learn concerning the fractal dimension and the porous structure yet. Now, that's the last team, the last four of the team, LCM. Here we have two of them. Vitor Gustavo used to work with polyaniline and artificial neural network. Ricardo with fuel cells reaction like methanol, ethanol over platinum surface without electric potential. Rodrigo now is currently in Professor Juarez' team. Leonardo is working with Professor Alejandro's team. Cynthia face all the TD-DFT computations. Gabriel is studying COOH and the hydrogenation of a small organic molecule onto platinum and platinum steam as well, platinum steam, with applied electrical field 1 volt and 0.5 volt, 1.5 volts. Vanessa is studying the Dirac cone between the carbon nanotubes and linear carbon chain as well. That's the guy Marcos Vinicius, who studied the crop the imaging and belong all the computation using finite element method. Eric performed many papers of that, one of titanium oxide, for example. This is a new study. We are looking for some scholarship yet to design some new experiment for him. And Vanessa is studying some absorption of water over metallic multilayers covered with iridium and applied potential as well. And we would like to see the start tuning effect. The first order they start tuning, and second order they start tuning effect as well. So I'd like to thank all of you still right now, and the Cine, all the Cine organized committee, and my co-workers, Professor Woodson, Professor Gustavo, Professor Leonard, Eudes Filete, Dennis Jackman, Hélio from UFMT, Professor Leandro from UFAM, who pay everything, CNPq, FAPEMAT, Senapad, CAPS, and thank you very much.
Professor Renato, excellent presentation, a class, in fact, in my opinion. Let me have a look in the chat. For now, we have one question.
Isn't it?
We have one question for now, but I have to encourage the chat, the people in the chat to ask questions, because it's a great opportunity, because we have been talking with a great specialist in the area, in this field. Professor Renato have a lot of knowledge in the electrochemistry, modeling, and so on. So, but if I may ask one general question or begin. And during our presentation, I have took some notes. The first one, considering the energy and power values that you present in the first paper of your presentation, paper with Carla Real, considering the great energy and power values, you believe supercaps can be able to replace batteries at some point or some time in the future, or even considering sodium batteries? How do you think?
I don't believe so. I think that the purpose of the supercapacitor battery is quite different. I mean, it's very different indeed, because the diameter of pores is different, and the coefficient diffusion of the species in there from the supercapacitor and battery must be different as well. So in a month, we have some shutdown, for example. We have the supercapacitor, we have a fast discharge and the charge, for example, to supply this device, for example, this notebook in here. We have the supercapacitor, and so as we take the battery. So once the purpose is quite different, we have all of them joint working together. I think we have better hybrid device, cars, and all engineers device working better with both. And although the engineer of them looks like similar, we have anode and a cathode and a membrane separating there, and the carbon materials and lithium, main part of that lithium is the same. Although the engineer looks like the same, the physical chemical properties is pretty different. I mean, it's much better. We have a constrained porous diffusion for battery compared to supercapacitor.
Maybe the ideal scenario is working together to...
Yes. Exactly.
Professor Renato,
two extremes of dragon plots.
Tua Nan Lorenzo, thanks you for the presentation, for the talk. And he asked, in the beginning, you showed different techniques on different time and size scales. How do you integrate them? Is it possible to correlate all scales? I think he's talking about time constant, different time.
Yeah, the time constant. It's not an easy question. It looks like the physical's holy grail, the equation of the everything, because we have some fundamental electromagnetic dynamic and quantum mechanics, and we have some different equations for the kind of things. I don't believe so. Up to date, we have the hybrid method, isn't it? Like KMM, when we have DFT and some hybrid one like molecular modeling, dynamic, and even Gaussian, it's possible to do that. But if you have a large time constant, like finite element method, you have a pore obtained from the electron microscopy, you have a pore, and you have a time domain in there, which is around microsecond, isn't it? And you have probably only close the time constant. If you separate time constant orders of magnitude, it's not possible to correlate in there. For example, finite element, we have time constant of microsecond. And the injection of electron like organic, like a benzene, like a cyanide onto titanium oxide, the injection of electron like semiconductor, isn't it? Solar cells, and you have femtosecond, picoseconds. It's not possible. I don't think so to correlate both of them. Closed time constant probabilities, yes. Even with separate programs like Console and Gromax, I think it's possible.
Okay.
Closed time constant. Orders of magnitude separate, I don't think so, not yet.
Okay.
That's a really good question.
Yeah.
Guys who work to integrate software, it's a tough task.
Yes. I'm not seeing other questions, so I will give a question for you. Maybe a more general question too. Yesterday, we have talked with some partners of our group, partners of industry, and we have talked about vehicle electrification. It's a hot topic. Yes, we have talked about the main ideas. How can I say? How the scientific or how can researchers can help the industry to achieve this goal, né? Okay. So
you are frozen, Rafael. You are frozen. Your
sorry.
Your imaging and your voice is frozen.
Oh, sorry.
What is the hot topic from the guys from industry? Which is the hot topic? Vehicle what?
Electrification. Vehicle electrification.
Yeah.
Okay.
Like hybrid vehicles in the near future.
Maybe my headphones is so good. So I have to ask you, how do you believe this modeling and electrochemistry can help the industry to achieve this point. How do you think? What do you think about this STEM, vehicle electrification, and how can modeling and electrochemistry can help?
I think that the main purpose of the computation is to save time when it's necessary and improve time when it's necessary. I mean, for example, all of us know that for some battery we have carbon, and we have mutual carbon, but how many mutual carbon nanotubes? And we have graphene, but how many layers of graphene, for example, the pack of graphene? And we have carbon, Vulcan, carbon, pyrolytic, carbon, another kind of carbon. And we have oxide. We need some oxide to release and to have this kind of channel. So we have all this transition method here. We have titanium, vanadium, niobium, thallium, hafnium, uranium, manganese, iron, cobalt, nickel, copper, zirconium, etc., etc., etc. So I think that the main purpose of the computational is to save time. It's possible to screen, like we did in the lithium, sodium, potassium, rubidium, says, hey guys, we have the best performance over cesium. Yeah, but it's impossible because cesium is quite large because we use lithium, the first one, because it's smaller, have a Stokes radio larger, but it's smaller. So we have cesium, yeah, but the computation towards cesium. So let's put efforts in the cesium one. I think the computation, the main whole of the computation is in applied field like the engineering, and have a device properly, is to save time and give directions. Like the direction for supercapacitor, for example, is try to perform some supercapacitor using cesium. I mean, not something that is quite hard and impossible to obtain experimentally, but something realistic that is possible to obtain. That's why I pay attention and I strive for all my students, let's narrow the band gap between the experimental and theoretical. It doesn't mean you have a theoretical and make some computation, hey guy, I'd like to have a nanotube made of, made of fluor. A nanotube made of uranium. Yes, uranium have a really good property because it's a perfect nanotube. Yeah, guy, but uranium, it's not possible to synthesize that one. So we must learn the experimental data, and experimental must to learn theoretical data. That's the main problem I see to have an increase in development for the engineer, because if I'm an engineer, we mean something applied, isn't it? It's not like in our dream, increase the property or would like to see how many watts in this lithium. No, I mean 10 hours straight in this battery. I mean one iPhone for 1 month battery for 500% state of charge. So I think that the computational must go in this direction, not only take a look in what happened in the experimental one and try together. But it's difficult. I mean, it's quite difficult because looks like the experimental theoretical works in a different vectorial subgroup space. So we need to narrow this band gap.
Yeah, it's a hot. How can I say that? It's a great discussion. We have to try to turn this more to approximate the industry and academy in this paper that you present in the first time, considering batteries and caps. It's so important for that.
Yes, and we have so many others kind of answers and the time concept of the system when we face computational and experimental together, even for increase the impact factor of the journals. Yes, but increase impact factor, yes, I have a highest impact factor. All right, it's pretty nice. And indeed, it's really good. But I mean, and what about the device? What about the notebook? What about the battery? What about you go to the internet and say, hey man, I have a system here if you design this one, if you pay my idea, you have a battery for 100% increase in the capacity. So for that one, I think we only have work together.
Yes. In this context, considering that, what do you think about titanium oxide that you already presented today? This can titanium oxide can be a great anode for batteries. It's have a great potential for be real commercial.
Titanium oxide is fantastic. It's just fantastic. Titanium dioxide, you have nanoparticles, and you have especially titanium dioxide nanotubes. And what about the main problem having battery? When you have the charge and discharge, the charge and discharge, all of us know that the boundary, the gray boundary, trying to split, and we lose the contact, isn't it? We have the large increase the molar volume and decrease the molar volume. We increase the molar volume and decrease the molar volume because we have a unit cell and you have a lithium get inside and lithium outside. As soon as you use the battery and you increase and decrease the molar volume, you have the boundary split and you have the ohmic drop, isn't it? Where electron is not possible to go to here to there because in the first moment you have this one and you have that one. Because it's organic for sure, but titanium oxide is inorganic. For obtaining titanium oxide, you must put in an oven, in a furnace for 600 degrees, 700 degrees. So it's an inorganic material, it's very hard. So you have a real release of a channel to get inside as amount of lithium as you want, and need to get inside the titanium structure. Most of the time, tetragonal, it's A, C equal and C different. And it has in Hood field, is quite possible as well, because you have a C large and a C lower, and you have the release of lithium. You get lithium inside and lithium outside. It's a really good material. And another really beautiful point, if you have 1 millimeter square of titanium nanotube, you have thousands and thousands of nanotubes. Because it's nanometers, you have 10 nanometers of pore, 100 nanometer. It's possible to tune, it's possible to control. So you have an array. You have all capacitors put together in a series. You have an array. Like you have a straw, you have a pack of straw, you have a pack of nanotubes. You have a pack of this one. So it will increase the performance and the capacity for both of them, for supercapacitor, pseudocapacitor, and for battery as well. Oh yeah, but I work with, with solar cell, and for solar cell as well, because many generation of solar cells using titanium dioxide, because we have 3.2, 2.8 electron volts, but if you doping, you can decrease the one. So nowadays we're studying a lot this last kind of solar cell. I forget the name, this last generation of solar cell, but for many years, from dye solar cells and polymer solar cells, the guys put titanium dioxide as well, as nanotube, as nanoparticle as well.
Thanks for.
So I think it's a really good material for both energy storage and energy conversion.
Okay. I take a look in the chat. I'm not seeing any more questions. We have to talk about the titanium oxide later, because we are looking to try use that in our batteries.
And it's very cheap. It's very easy to obtain titanium nanotube as well. It's very simple.
Have to talk about
it's a cheap material because a plate of titanium is cheap. It's a cheap material, and the way to obtain is quite simple. It's very simple, extremely. And the functionality from the electrochemical point of view and from theoretical point of view, because you already have a tube, is fantastic. Titanium nanotube is fantastic. From using finite element, from dynamic molecular dynamic, from density functional theory as well. It's a great material.
We have been trying to synthesize silicon carbide to use as a node for batteries also. What do you think? Do you know this
No,
node?
no. Silicon carbide.
Yes.
Yes, what about the crystalline structure? It is cool,
It's,
tetragonal, do you remember?
I think it's tetragonal. And
Tetragonal.
yes, but the main point here is the silicon carbide. I think that the right name. Silicon carbide have 4 or 5 times more capacitive
Oh, really?
than
For pseudocapacitor.
for graphite, considering as a node for batteries. So it's
Mm-hmm.
so great, but
For batteries.
have some problems because silicon by your by
And what
yourself,
about the morphology? The morphology is what kind? Nanoparticles, nanotubes, nanosheets,
nanoparticles,
nanoparticles?
yes.
Interesting.
But you can find different types in the literature, but nanoparticles is the better, I think.
Your route of synthesis obtain nanoparticles.
We have been trying.
You have been trying. Keep going.
But
Oh, let me see the results after.
yes, we have to talk about
You have impedance as well.
yes.
Yes.
We'll try to do that. For now, we're just trying to synthesize the composite, but we'll do all of electrochemistry analysis. We have been
The protocol. Yeah.
yes.
But did you obtain some impedance already?
Sorry?
Did you obtain some impedance already or not?
No.
No, not yet.
Yes.
Your phone is turned off, Aguinaldo.
Oh, no,
Yeah.
Excuse me. We have reached the limit of our time here for our live audience.
Sorry.
Yes, thank you so much for the great talk, Professor Renato. It was a great pleasure.
Thank you.
And thank you so much. It was
Thank you
a
very
great
much
pleasure indeed. Thank you, Rafael, for being the chair as well. I hope to see you next time. Thank you so much.